Hello. So on this video, we're going to start on section 5.2 in the book. We're going to introduce a different way of measuring angles. Right? So in the previous videos, we've been using degrees. Now we're going to introduce a new angle measurement, which is called a radian measure. Now, this angle measurement is very useful in calculus, in physics, and in engineering for a lot of reasons that we're going to see in a moment. Right? But for now, let's just define first, how do you define a radian measure? So what is 1 radian equal to? Right, we know that 1 degree is 1/360th of a circle in terms of rotation. So what is 1 radian? So let me give you the definition of 1 radian, and then I'm going to show you in this picture that I drew of a circle because it's easier to understand with the picture. An angle in standard position whose starting and ending rays create an arc of length equal to 1 radius of a circle has a measure, right, that angle has a measure equal to 1 radian. So that's the definition. Let's see how it looks like in an actual picture. Right? So here in this picture that I drew, I have a circle on the XY plane. And then that circle has radius 1. We'll see later that the radius doesn't matter, right? But in this case, I'm working with a circle of radius 1. I have an angle in standard position, right? The initial ray, the one in red, is on the positive x-axis. Then I rotated that a little bit until I got to this ending ray in purple. Now that creates an angle theta. Now this angle theta has the property that the arc that it created on the circle, which is what I highlighted in green here, let me highlight it again. This arc here, if you were to stretch it out and measure it, this arc would have a length equal to 1. In particular, we have a length equal to the radius of this circle. So anytime you have an angle with that property, right, that the length of the arc that it creates on the circle has length equal to the radius of the circle, then the angle measurement for that angle is defined as 1 radian. Okay. So it's a little bit complicated, right? But you'll get used to it very quick. Basically, it's just how do you relate an angle with the arc that creates on a circle and that measurement of that arc. As long as you understand those 3 concepts, you can understand easily what a radian is, right? So this angle theta has an angle measure of 1 radian because the length of that arc is precisely equal to its radius of the circle, which is equal to 1. Now, notice that then, anytime we're thinking about defining an angle in terms of radians, it is intimately tied together to circles, right? We cannot think of radians without thinking about circles, right? So similarly to how we did it with angles, with degrees, however, for degrees, it wasn't that tight of a relationship. Right? Here it is because here we're interested in the length of an arc created by an angle by its initial and ending rays. Right? You want to know the length of that arc. Right? So it's intimately related to circles. Now, there is a formula to calculate radians. And it's a very nice formula. It's one that we're going to be using for the rest of the semester, basically, while we're talking about angles. And when we're working with trig functions, etc., we'll mostly be working with radians. So given a circle of radius r, right, and an arc traced out by an angle, right, so you can look at this picture while I'm reading this, you can find the radian measure of the corresponding angle using the following formula. Theta in radians, specifically, this only works if theta is in radians. This doesn't work if theta is in degrees. So let me make a note of that. Theta in radians is equal to the length of that arc created on the circle divided by the radius of the circle. And that's what I drew here. I drew again an angle theta in standard position, right? So the initial ray is on the positive x-axis. The purple ray is its ending ray, right? Given those rays, it creates an arc on the circle, right? And I labeled that arc by this symbol S, right? So the green part is the arc, that's S, right? And I have the radius as being R, right? So given this information, if I wanted to know what is the measurement in radians of the angle theta, all you would have to do is calculate the arc length S, or the length of the arc, and divide it by the radius of the circle, right? And that's precisely what this formula is telling you here. And again, let me note that this only works for theta in radians. Okay. Now, I mentioned in the previous slide that it doesn't matter what radius we're using for the circle. Right? So in this case, I gave you an example of a circle of radius 1, but it turns out that it doesn't matter what radius we use for the circle. Right? And here I explain it. Right? So if theta has a radian measure equal to S over R, and we know that's the formula, we know that's the definition, that's how a radian measure is defined by this formula. If we change R to a new radius, R prime, right? So that's what I wrote there. So let's say we increase or decrease R, right? We change the radius, right? Either make it bigger or smaller. If we increase or decrease the radius of the circle, then we're also changing the length of the corresponding arc. So let's say that we're also changing S to a new arc length S prime. Right? So we change R to a new radius R prime. That changes the length of the arc from an arc of length S to an arc of length S prime. What does it mean when I say that it doesn't matter what angle you use or what radius you use, that theta in terms of the radian measure of the angle is always the same? Well, this is what I mean. If you take the ratio of S prime over R prime, it is exactly equal to the original ratio, S over R. What does this mean? It doesn't matter what angle you use for R, right? Since the ratios are always the same, right? You can use any radius for R. So in particular, that's why I used radius 1 in the previous example, because it's the simplest radius to work with. But that's why I am allowed to always work with a circle of radius 1. You could work with a circle of radius 3, radius 4, etc. The radian measure is always going to be the same. The ratio of this green arc that I drew here, the ratio of that green arc by the radius of the circle is always going to be the same, right, for a given angle theta. So as I stated, what does that mean for us? We will always use R equals 1 for the radius of the circle, unless stated otherwise. And another thing that tells us that we get from this formula is that radius are unitless. Why are radians unitless? When we talk about degrees, you notice that I always write the degree symbol, right? That's the unit, just like we have length measured in centimeters or something like that. However, notice that radians are defined as a ratio of distances. So if we just assume that these two distances have the same measurement, and if they're not, just convert them to have the same measurement or the same unit measurement, then those units cancel because we're dividing. So whatever we're left with here has no units because they cancel out. And this is one of the reasons why working with radians is a little bit better than working with degrees. But with degrees, you always have to make sure you keep track of the unit. You always have to write degrees. For radians, since they're unitless, you don't have to write anything. So for example, if I write theta equals 7, and I just write it like that, since there are no units, you immediately have to know that this means that this angle is measured in radians. If I want to measure an angle in degrees, I will always write the unit. So if I write the unit degrees, then this is actually measured in degrees. Otherwise, if there is no unit written, assume that it's in radians. Okay. So this is why, again, it's preferable to work with radians, right? Because you don't have to worry about any degrees. And then you also have this really nice relationship. Right? You have a formula that relates the radian measure, so the angle measurement, the arc length of the corresponding arc, so the length of that arc, and the radius. So you have a really pretty formula that relates all of this information, which we're going to use later, right, into this compact formula.